All right, today we're going to talk about capacitance. We're going to introduce this idea. The basic idea of capacitance is really simple, and it is that there is a relationship between the amount of charge present on a surface and the potential of that surface. Now, that should not be a surprise to anyone. The reason it shouldn't be a surprise is because you've seen this already. When we were talking about potential for a point charge, we saw that V equals 1 over 4 pi epsilon naught Q over R. And you can see there's a direct one-to-one relationship between charge and potential. So that's for a point charge. Now, in general, there continues to be a relationship that is a linear relationship between charge and potential. And we can express that this way. Charge is equal to some constant times the potential. And that is a really simple equation. That's called the capacitance equation. And we will use this equation repeatedly when we get in farther into capacitance. But the C here is just a constant. It's a constant proportionality that depends upon the geometry of the situation you're talking about. Whether you're talking about parallel plates or you're talking about spherical capacitance or some other type of thing, this C varies, but it is a constant of proportionality that is fixed for any specific geometry. And hopefully that'll make more sense a little later on. But the C here is called capacitance. Okay? So that turns out to be our definition of what capacitance is. Now we can use this equation. If we solve for C, we just see that C is Q over V, and that will allow us to solve for the unit, and we can see what the unit for capacitance looks like. That's going to be Coulomb per volt for units. So that unit, Coulomb per volt, is what the unit is for capacitance. However, that's one of those units that we've named something else. We call this a Farad. And we abbreviate that with the symbol capital F. Now, 1 farad of capacitance is a fairly large amount of capacitance. So typically, you're going to be dealing with millifarads or microfarads or nanofarads or even picofarads. So small amounts of capacitance are typically what you would deal with if you're dealing with a relatively simple circuit. Capacitance is going to be the first of the things that we talk about whenever we're heading towards a discussion of circuits. So we'll talk about capacitance first, then we'll talk about resistance, and then we'll start talking about how to solve for circuits and so forth using all this information that we're learning here. A device that possesses the characteristic capacitance is called a capacitor. So a capacitor is an electronic device that its main characteristic is its capacitance. Now, let's say that we have an example here of 2 parallel plates. Let's say that we have, and you've had a foreshadowing of this already. We've talked about charged parallel plates. But let's say we have a flat parallel plate, a flat plate here that has some area, and we'll say that that area is A. And then nearby we'll take another plate and we'll put it over here, and it has also an area A. So we have these 2 plates. They are parallel to each other, and they are separated by some distance here, which we'll just call D. All right. Now, if we put some charge, let's say we put some charge on this plate, and the amount of charge is plus Q. And then we put an equal amount of charge over here, but with opposite polarity, so we have minus Q on this plate. Now, the entire system that you see here has a net charge of 0, but the charge Q is the same on each of them, quantity-wise, but opposite in polarities. That's going to create, then, a potential difference between these 2 plates. Now, that just makes sense that that would be the case. So there's going to be some potential difference between the 2, which we'll just call V there. Well, V then multiplied by the capacitance of this system is equal to Q. And remember, Q here is not total charge. Q here is just the charge on one plate. So Q is equal to the capacitance of this system times the potential difference between the two. All right, now let's think about this situation right here a little bit more and a little bit more in depth. Let's look at our parallel plates kind of from the side here. So we're looking at them edge on. And let's connect a wire here, and we'll connect a wire up here. Now, our wires in this course, we assume are perfect wires, so they have no resistance. They don't cause any problems by their existence being connected here. So here are our two parallel plates. What this is a capacitor. So this is an example of a capacitor. At this point, it has no charge on the plates, so let's connect it up to a battery. Now, a battery is a device, if it is working properly, let's draw it like it's a car battery here. If it's working properly, it maintains a potential difference between the poles here. So if this is the positive terminal of the battery, this is the negative terminal of the battery, and we'll say this is a 12-volt battery like a car battery, then the plus here does not mean plus charge. The plus here, in the case of the battery, means that this is the higher potential pole of the battery, and then the negative indicates that this is the lower potential pole of the battery. But the potential difference between the two poles is 12 volts. Now, you know that if you have an electric field, and we'll draw this constant and uniform electric field here, and then if you take a positive charge and place it in the electric field, that positive charge, if it's free to move, is not going to sit there. It's going to move in the direction of the electric field. So the way that we say that is that a positive charge moves from the high potential area to the low potential area. And we have discussed how if you have a equipotential surface, that would be a plane in this case, and here's another equipotential surface, then this is the higher potential and this is the lower potential. So a positive charge will move from the higher to the lower potential, and it just does that naturally. Well, we can do that here because this battery, like I said, if it's working properly, it maintains a potential difference between the poles. No matter what you do to the battery, it will have a 12-volt potential difference between the poles. It's converting chemical energy into electrical energy and creating that potential difference there. Well, let's run a wire from this pole up to that wire, and then a wire from this up to that side. Now what we have done is we've created a potential difference between these two plates. So if we imagine a positive charge as being the charge that moves, now technically speaking, you as a good physics student know it's not positive charge that moves through wires, through conductors. It's the negative charge. It's the electrons that move. Nevertheless, if you talk about a positive charge going in that direction, that's the equivalent of a negative charge going in that direction. From a measurement perspective, now there is a difference here, but from a measurement perspective, if you're just going to measure the movement of the charges, then you can't really tell the difference between positive going that way and negative going that way if you're trying to measure a current. And a current, if you recall, is just moving charge. All right? So in this case, imagine what happens is that we have a current of positive charge that begins to flow. It's moving away from the high potential toward the low potential. Let's label that current I. That'll be the symbol we'll use for current here. And I is defined as dq dt. dq is charge per time. So if you have a piece of wire and you have charges moving through it, if you set up let's say you set up a gate here and you're marking the number of charges that pass by in a second, the number of coulombs per second that pass by, that's what the current is. So look at the unit here. Charge has unit of coulomb. Time has units of second. That is a unit for current, coulombs per second. That is also one of those units that we've renamed something else. We call it an ampere. And you just pronounce it oftentimes as amp, and it's symbolized as just capital A. So that's what we've got here. We're assuming that it's a positive current flow moving in that direction. Now, anytime you assume a positive current flow, that's called a traditional or conventional current flow. So for the most part in this class, we will assume that positive charges are moving, and we'll talk about conventional current flows. But once again, you as a good physics student understand that it's not the positive charge that moves, it's the negative charge that moves. So what's going to happen here is the charges are going to come along here and get to this plate. Now, there's a gap between these two plates. This is the lower potential side. This is the higher potential side. But the charge trying to get to the lower potential has to stop right here. It cannot bridge that gap. So what happens is the presence of this positive charge here induces a negative charge here. Now, where did that negative charge come from? Well, you've got all of this conductor here. So the negative charge moved in that direction to get as close to that positive charge as it possibly could. So here you have these two charges that are right next to each other. The negative was induced by the presence of the positive, but the negative had to come up in that direction. Well, remember what I just said, a negative moving in that way is really the equivalent of a positive moving that way. So that same current that went up this way looks as if it jumped across and continues on through. Well, that is called a displacement current. It's not really a true current. You can call that a displacement current through the capacitor. But nevertheless, from a measurement perspective, if you're just measuring current on this side and current on this side, those two currents would be the same. All right, now think about what happens given enough time here. We've got this positive charge that moves along here, and there's already a positive charge there, so here comes the next positive charge. Well, the next positive charge is being pushed by the potential difference of the battery. The next positive charge wants to get as close to the lower potential as possible, but now there's a positive charge there that's going to push back a little bit. Nevertheless, the battery is probably strong enough to push a couple of charges over, which induces another negative. But then the next charge comes, and there's more resistance, there's more pushback due to the presence of the positive, but let's say the battery is strong enough to push, and that induces this. Well, that process is going to continue on, positive, 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 negative, 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 and you're going to have a buildup of charge on both plates. And the charge over here, let's call that plus Q. The charge over here is minus Q. Well, that charge is going to be equal but opposite polarities. And it's going to build up on both plates. But think about what's ultimately going to happen. The battery has some limited potential difference between its poles. It's not infinite. So one time after the charge is built up on the positive plate here comes the next positive charge, and there's just barely enough energy to push it through, which induces the negative on the opposite side. But now the next charge comes along, and it can't make it. All of these positives here are repelling the flow of that positive charge up. So there's just not enough energy, not enough potential difference between the poles of the battery to push even one more charge up there. And now the current has stopped flowing. So if you were to graph the current flow, let's say you graphed the current that was flowing here versus time. Here's t equals 0. Well, it started off at a high value, some maximum, we'll call that I max right there. And then over time, it decayed. And it decayed to nothing, to 0. Well, this type of curve is not like an inverse square or an inverse. This is a decaying exponential. So you would write that as e to the negative and some coefficient, we'll just call it alpha right now, times t. There would probably also be a coefficient out front, and that would be I max. We'll just call that I. I sub m is I max right there. That is what the equation would look like that describes this current flow. You can see it is a function of time. As time goes by, it decays like that. The I sub m, well, that's the maximum value. And the alpha that you see here, that is related to how fast it decays or how slowly it decays. That would be a time constant that's related to this curve here. So the curve could do this. A curve could do even this, you know, and take a long time to decay out here. Which curve it is depends upon what the alpha value is. But nevertheless, in each case, the curve is similar in that you have a decaying exponential for that is the equation that describes the current through the capacitor here. All right? So you have a decaying exponential then. Okay. So there comes a point here in our example where there's no longer the ability to push the charge around. The current has decayed to zero at that point, at that time. And now the capacitor is fully charged. Well, when is that going to occur? That will occur when the potential difference between the plates here is equal to the potential of the battery. So that occurs when the potential difference between the poles is 12 volts. All right, now if you take and disconnect all of this, let's disconnect the battery. And what do we have? We have a capacitor that still has charge on its plates. It still has plus Q on one plate and minus Q on the other plate, and a 12 volt potential difference. Now, that's going to remain there. That doesn't bleed off into space if we're assuming that this is a perfect capacitor and there's no reason for it to lose that energy that is stored in there. But because you have these charges here, you're going to have an electric field that points from the positive plate to the negative plate like that. Well, in that region right there, there is energy. The energy is stored in the capacitor. And you can use that energy to do any number of things. That is stored potential energy right there. Now, unlike the battery maintained a potential difference between its poles. Remember, if it's working properly, it will always have 12 volt potential difference between its poles. But if I were to hook this up to, let's say, a light bulb, here's a filament for a light bulb, might look like that, this old school light bulb. And we'll enclose this in some sort of glass container here. And we'll make this is like a flashlight light bulb, one that you would screw in. We'll take one of those wires and run it down here to the bottom and connect it. That's where you would connect to this wire. And then the other end goes here to the side, to the metal portion, and connects that way. So down here below that line, that's the metal. But this wire that's running down is not touching the metal, it's touching this bottom terminal here. So if I connect this wire to there, and then I connect this wire to there, well, now this potential difference of 12 volts has a path through which it can flow. So think about what's going to happen. If this is the high potential side, conventional current flow is going to begin to flow this way. And it's going to go up here, and it's going to go up through the filament. Now this is a light bulb, so it has a filament that when you pass a current through it, it begins to glow. So as it begins to glow, what happens is it emits light. So that light then is electromagnetic radiation, and that represents energy that is now escaping the system. So that light is flying off into space here. And the current continues to flow on around, back here, and go back that way. But over time, because we're losing energy out of the system, the energy that was contained here in the capacitor is slowly decaying itself. So what does that mean? That means ultimately the current is going to stop flowing. And the capacitor is going to be drained of its energy. And because it's drained of its energy, the light no longer shines. So that means the capacitor has a limited amount of energy in it. Whereas if you hooked up a battery here where the capacitor was, so take out the capacitor and put the battery there, now if the battery's working properly, it maintains a potential difference between its poles, and then there's no energy loss between the poles of the battery, and this thing would shine its light for continuously, assuming that, once again, it's a perfect battery, there's no energy loss. Of course, in reality, there is no such thing as a perfect battery. So over time, over a long period of time, the battery would eventually die and this light would no longer shine. But nevertheless, the point here is the battery works to maintain that potential difference between its poles, whereas the capacitor has only a limited amount of energy, and once it bleeds off, then it's done. It doesn't get that energy back because it doesn't convert chemical energy into electrical energy the way a battery would. It just holds charge. And once the charge has dissipated through current flow and left the system through electromagnetic radiation like this, then there's no more energy there. It can't make energy from chemical energy like a battery could. All right. Well, then a good question might be, well, how much energy can be stored in a capacitor? Well, let's talk about potential. Now, from the definition of potential, we know that that is the work per charge. To mathematically define potential, we can define it this way. It is energy per charge. So in a differential form, this is a definition of what potential is, just like this is a definition of what current is. Well, if you take this equation and you solve it for du is going to be V dq, like that. Now, du is the energy. So if I were to sum up all of the energy for all of the charges that exist inside the capacitor, then I could write it this way. Let me redo that. The total energy U is just equal to the sum of the individual du's, which is equal to the sum of V dq. Now, V for capacitor can be found from the capacitance equation. Remember, the capacitance equation is Q equals C times V. So if I solve for V and plug that in here, this is the integral of Q over C times dq. Now, C is a constant, so we can factor that out. And when we integrate Q dq, you could say that's primes there, and we're going from 0 to Q to give it a definite integral. But the point is, that's going to end up being Q squared over 2. So the amount of energy that is contained within the capacitor then is equal to Q squared over 2C. You can see the energy is related to the capacitance and the amount of charge present. But if I solve, let's say that I take C and I plug it in here for Q, then that can also be written as 1/2 C V squared, like that. So there we have two expressions for the total energy that's contained within a capacitor. So that tells you how much energy is stored in the electric field as potential energy in the capacitor. All right. Now, let's try to figure out how to determine capacitance for a parallel plate capacitor. And I think I can do that in just this little space right down here. First of all, we have already found what the electric field is using Gauss's law for a capacitor. If you don't recall that, then just think back. E, for the electric field for a parallel plate capacitor, is equal to sigma over epsilon naught. Now, sigma was charge per area. So if we have a surface area for our two plates, then that's Q per epsilon naught over A. That's charge per area. So that's what sigma is, charge per area there. Okay, well, that's the electric field. You also may recall that there's a relationship between the electric field and the potential, and we determined that is equal to E times D. Because we have a uniform electric field in here, the distance between the plates, D, means that E times D is what the potential difference is between those two plates. Okay, well, if I take E and I plug it in here, I end up with Q over epsilon naught A times D. Now, remember, this is the capacitor equation. This is just a relationship that we derived based upon that and that, those two relationships that we've already determined. This from Gauss's law and this from the relationship between V and E. So if I rewrite this equation and put it in this form, Q equals some constant times V, well, what's that going to look like? Just solving for Q, Q is equal to epsilon naught A over D times V. So what's in parentheses right there, that is the C. Because this equation, the form of this equation, is the same as the form of this equation. So for a parallel plate capacitor, like we've imagined here, the capacitance is equal to epsilon naught A over D. Now, notice that capacitance equation does not depend upon anything like charge or potential or anything other than the geometry, the area, the surface area, or the distance between the two plates. And those are geometry dependent. I mean, you could change the area of the two plates just by changing the geometry of your capacitor. You could change the separation between the two plates just by changing the geometry of your capacitor. So the capacitance here is related to geometry. That's a general statement that will be true no matter the situation. You'll discover here in probably just a few minutes that capacitance always depends upon geometry. It doesn't depend upon things like charge or potential difference or any electric field. It just depends upon these values, some parameters that are related to geometry. However, this equation only applies to the parallel plate capacitor that we have here, because E is this for the parallel plate capacitor, V is this for the parallel plate capacitor. So if those two were different, you would get a different value for C, and you would have a different geometry as well. All right, one other thing before we go on, and I'll just do it here on the back side. C equals epsilon naught A over D is the capacitance for a parallel plate capacitor. If I solve for epsilon naught out of that, I get epsilon naught equals C D over A. All right, let's look here at this because the units here are going to work out to be this. Let's see, C has a unit of farad, D has a unit of meters, and area has a unit of meters squared. Now, one of those meters is going to cancel, and I have left here farads per meter. That means epsilon naught could have units of farads per meter. So epsilon naught, if you recall, is 8.8 0.85 times 10 to the negative 12th coulombs squared per Newton meter squared. So all of that right there is the same as farads per meter. So sometimes you will see this expressed in units of farads per meter. So if you run across that, don't be afraid. Nothing's changed. It's just two different ways to express the unit. And we had to learn about capacitance before we could express it in this way. Now let's go on and give you sort of a step-by-step procedure to find capacitance. Because we just did it for a parallel plate capacitor, so I want to write in general terms how you would find the capacitance for some situation. And it's a pretty easy process. It's like 1, 2, 3 steps. So step 1, what you need to do is you need to solve for E. Solve for the electric field. You need an equation that describes the electric field. And oftentimes, to do that, you need to use Gauss's law. So you'll solve for E using Gauss's law. And you know that Gauss's law is closed integral E dot dA is equal to Q enclosed over epsilon naught. Okay, when you do this, you go through the steps, you end up with E is equal to some function of Q. All right, so you're going to have Q in your equation for E. Then the next step is you plug that. So you plug E into the relation of V. And that V equals minus the integral of E dot ds. And once you've got that, once you go through the steps there, you got V equals some function of Q. Now those functions are not necessarily the same, so let's call that function 1 and this one will be function 2 right there. But you set those, you solve these in such a way so that you can set up the equation, solve so that you can set up the equation Q equals C times V. And what is in between the Q and the V, that is the capacitance. And that's what you would solve for. So for our example of a parallel plate capacitor, we saw that C equals epsilon naught A over D. The textbook goes on and it does several other situations. For example, for a cylindrical capacitor, C equals 2 pi epsilon naught L over natural log of B over A. Okay, well, what does that mean? That means you've got some cylinder here, that's the inner cylinder, and it has a radius of A, and then surrounding that you've got another cylinder here that has a radius of B. And the length of the cylinder is whatever it is, L. If you were to go through the process for the cylindrical capacitor, you would end up with this as your capacitance. The example for a spherical capacitor. For a spherical capacitor, C equals 4 pi epsilon naught A B over B minus A. And you want to know, okay, well, what is that? Well, you've got this sphere. Let's say this is the outer one. This is B, and then you've got an inner sphere that has a radius of A. And those have positive charge on one sphere and negative charge on the other sphere. Well, this is the relationship for capacitance then. Now think about this for a minute. Look at each one of these. These are 3 separate cases, very different geometry, but notice in each of these cases C depends not upon charge or voltage or electric field. The capacitance depends only upon the geometry of this, only upon how big the radii are, or how large the area in separation is, or how long the cylinders are in their radii. So all of these are independent of everything except geometry. They depend solely upon geometry. The textbook goes through a lot of steps here to derive these. I am not going to spend time deriving those, but you can look in the textbook and see how they're done. The one that you need to know and which you will use the most is going to be the parallel plate capacitor, though. So I would encourage you to do your best to know the parallel plate capacitor inside and out in all aspects, not just capacitance here. Okay, we're going to move on.